So, what gave you grief? Do not memorize that formula. If anybody's looked at this, very often I hear dry heaves, other manners of gnashing of teeth, saying of rosaries, that kind of thing. All this formula is a way of measuring skewness. So we've talked about bell-shaped data. Bell-shaped data, right? Bell-shaped data. What this formula is a way of measuring how far away from bell-shaped data is allowed to get before we don't consider it bell-shaped anymore. I apologize for using the phrase bell-shaped 3 times in that sentence, 4 times now. So basically what this formula does is it compares 3 of our favorite statistics, the average, the median, and the sample standard deviation, and it plugs it into this thing called the Pearson's something or other. There it is. Thank you, Christina. Pearson's second skew coefficient. And based off the results in Hildebrand's paper from 1986, great year by the way, based off his results from that paper, we decide if the number that comes out indicates skew or not so much skew. You got to realize something though. You got to realize something. When I asked the questions down here about these data sets that we had looked at in class already, you recognize these, right? LDL levels in men, you recognize the house prices, you recognize the bimodal, right? When you plug those numbers into the PSSC formula and get values out, you're making the call on skewness based on Hildebrand's article. That's Hildebrand's opinion. You see what I'm getting at here? It's the law as written down by this one gentleman who published paper 86, and as far as I can tell, there have been no follow-up papers, so it's used kind of like law, if you will. It's kind of like how we judge skew. That doesn't mean it's gospel, it means it's law. Does that make sense? Statistics is a creation. Statistics is a bunch of rules that have been created by people to describe data in the best way we possibly can. It's not like gravity. You drop something and it falls with a certain acceleration, and it always does. People didn't create that, it is. So the problem with this one is, you get results. We interpret them via Hildebrand, and you might counter that with your own opinion and say, nah, I don't think it's that skewed. That's okay. Make up your own measure. Make up your own measure, put a paper out, contest Hildebrand. He might be dead by now, who knows? 30 years ago. Okay? Sorry if you're Donald dead, Hildebrand. Anything in here give you grief? Let's get you warmed up, just in case some of you seem like you're asleep.
What were you saying?
What am I saying? I don't know. I'm just vomiting ideas up here. Here, I just lost it. Here are 4 distributions of data. Right here, right here, right here, right here. I think, since they're roughly bell-shaped, you could assume the averages are right above the highest point, which I think is not hard to believe. Which one of those shows the greatest variation around the mean? B. Greatest variation around the mean, let's be on it. 1, 2, 3? B. 1, 2, 3? B. That's only slightly marginally better. Yes, B is the most variation around the mean. Why? Who wants to put it in words for me? Why is it the most variant? Tim, go.
Its outliers are bigger than the
ones
that
nice.
don't have any outliers.
Oh, good for you, good for you. I like what you're saying. I can contest what you're saying. So I like what you're saying, because you're saying the further we get from average, there is definitely more of a presence of those data points.
The mean has value, or the less the mean is. But the one on the right's the mean's most accurate because there's no outlier.
Can I change the word accurate to starts with a P? Precise. Now, I didn't do a very good job of putting these graphs in, but essentially my point is that they all have the same average. If that line represents a unit of scale, the average of all of these is directly in the middle of it. So the average, accurately, on accurateness, we're hitting the average every single time. What we're not hitting is consistent. We're not hitting the average consistently. This is the least consistent. I think Tim's just voted that D is the most consistent. And it looks like maybe next least consistent, and then next least after that. So least variance, slightly more, most. Is that the vote for you guys?
Yeah.
So what you said was awesome. I think all of them have outliers. Even this one out here, it's hard to know without the raw data, but because the graph isn't zeroed here, that means there's a presence of stuff out here. There's just one of them. There's not many of them compared to that one, which seems to have more. Good, good. Tiff, go.
Well, I mean, I had chosen B, but your answer says D.
I put
Did I
order
put
of increasing variation, so D would come first. It has the least
Oh, I
variation.
see what you're saying.
You see,
That's
it all
right.
depends on,
Okay.
I may have phrased it differently in class
Right,
today.
right.
I'm actually glad I did. It seems like I'm trying to confuse you, I'm not. I'm just trying to get the conversation started.
Okay.
So increasing, since D has the least,
Gotcha.
it would go DCAB, I think.
Got you.
But if you go greatest to least, it would be
Right, I
reversed.
did,
John,
yeah.
go.
Isn't that just a wider range or a narrower range of X values?
Yeah.
Yes, I guess it could be. Yeah, I wasn't thinking of, I was thinking data. I had the process in my mind when we were calling X values. Yeah, more of the X values are here than here. The only reason I was thinking about that is you're assuming the same number of data points for all 4 graphs, which is a fair assumption to make based on what I just said to Tim. But here's the deal. Suppose this particular graph, right? Suppose this particular graph had 100,000 data points in it, and this one only had 10. You'd actually potentially have a narrower range on this one. Just by virtue of the fact there are so many more of them, so many more would be close to the mean. Where the 10 that are over here, there could be a potential outlier out here and out here. Where so over here you might say, well, 80% of them are around the mean. And here you go, yeah, but 95% are within 2 standard deviations. So all things being equal, what you said is 100% correct. But just realize it's not gonna, that will be gospel, so to speak, depending on the sample size. That's why I was trying to think about before I just give you an answer, I had to think about, okay, that sounds brilliant, but could there be an exception? In theory, what you got is perfect. Cool? You guys okay knowing how to get the standard deviation out of the machines? One of our stats, we like those. We like those. You know, once the number comes back, what it means? In case we did a refresher, we'll look at that again when we do the number of states here in a second. Go. Madeline, go.
I feel like it's a little dodo, but the verbiage versus the Greek letters is very confusing to me.
Okay, give me an example.
Standard deviation, I still don't like look at my calculator and know which one I'm looking at.
Oh, gotcha, friend. Gotcha. So when you're looking at the, let me grab a, we'll do it together in class with real data, but to answer your question quickly, let me just see if I can Google real quick a TI-83 stat screen. TI-83 stat calc screen. Let's see if we get image-wise. Perfect-ish. There it is. We'll use that one. A little bigger, maybe? Okay, so this is the main screen you would get once you hit one bar stats, enter. Okay, what's the, whatever this data is, I have no idea. What is the average?
38.4.
This that guy right, this is the top number, top one that comes out. What can we do with these two right here for the most part?
Ignore them?
For the most part, ignore them. They're interesting, but they don't give us what we're studying in this class. Okay, these guys right here.
So the top one is sample size?
Yes, ma'am. Sample standard deviation.
Sample standard deviation. The second one is
Population standard. And please, friends, ignore this one for right now as well.
Okay.
Because I'm not going to give you, I'm giving you samples. Statistics is all about samples. So in other words, for this screen, honestly, look at that and look at that. You know how many data points you put in. You don't have to look at n equals 20.
Right.
But this guy, X bar and S are the two ones. And if I could, Madeline, if I could, I would get into your TI and recode it so it only gave you those two things, but I can't.
Okay, yeah.
So.
I was just like,
It's okay. That's okay. No, not at all. It's another language. It's Greek in particular. And we'll come back to that Greek little sigma. We'll come back to that Greek little sigma, and we'll deal with it when the time makes sense to deal with it. It doesn't make sense right now. Please, Tim.
Do we round, or do you want us to?
I'll tell you what to round to.
Put the okay.
I'll tell you. Honestly, it doesn't make any sense to report this entire number as an answer, because that implies that you have precision you're not entitled to. I mean, every time you add a decimal, you're implying that your measurement device is 10 times more precise than it was without that decimal. That's kind of ridiculous to
I've
think
just been
about.
rounding.
That's okay, please do, and don't get hung up on that. I'll tell you what to round to on exams. I know that primer quiz you just got back, some of you got docked points because you didn't round to the correct space. Well, that's the only time you'll get nailed that hard, that consistently for not rounding correctly. Just, you'll never write down an entire value. That's just silly. It's just silly. Especially because the original data probably was only accurate to the whole number. Which means technically you should round this to the whole number, I guess. But don't worry about that. I'll get you taken care of. Madeline, make sense?
Yeah.
You guys make sense what you're pulling off of that? And there's a screen below that we're actually going to get into today. I want to talk about the numbers that are under that, because the median's down there, as you remember. But there's also some other stuff down there that's super fun to talk about. And part of statistics as well, but not for your example. Cool? Good. Glad we could find that. Thank you, Google. All right. So variation's okay?
Yeah.
Hell yeah it is. Do not memorize any formulas. Please, dear Lord, don't memorize formulas. Pearson's is a great formula. I would never have you memorize it. As a matter of fact, I'm going to have you use it in your Excel. You're actually going to figure out what the skew is for an extra credit point. How to find that skew in Excel. So you'll see it in the footnote. You'll see it in the footnote. So. Okie doke. Let's chit chat about your exam a little bit. Let me shut this down for now. Stop and start the camera.